Good afternoon, everyone. Thank you for joining us at PyData LA. My name is John, and I'm going to be introducing everybody to a talk called Extending Pandas with Custom Types, led by Will Aid. If I could kindly ask you all to please silence your cellular devices and turn your notifications off, that would be great. And without further ado, let's give it up for Will Aid.
Hey everybody, thanks for coming today. Super excited to talk to you about extending pandas at the very first PyData LA. So just a quick introduction to what this talk is about. With the last major release of pandas, we introduced a new extension interface to the system. So if you're asking, why do I need to extend pandas, this is a good place to be. The purpose of this talk is to just explain that in a little bit more detail. We're not going to go down into like how to actually do it with the new interface. So I'll give you some resources to look at that going forward. But just really want to get you acclimated with this new feature, what it is, show some examples of where it might be useful. With the caveat, this is brand new. It's still under development, so I wouldn't call it completely stable at this point. But myself and a few of the other devs of Pandas think this is going to be a pretty killer feature going forward. So with that, let's talk about the motivation for this. Pandas historically bound to the NumPy type system. NumPy, great package, obviously responsible for a lot of the other packages' success that you've heard about here. But like any package, it's not without its limitations. So integer and Boolean types, if you try storing missing data in an array with either of those types, good luck, it's not going to happen. And for things like categorical data, datetime with time zone, types like that, they don't exist in NumPy. They do exist in Pandas, which you may be familiar with, but that's not done without great effort to change the internals of the package to be able to support that kind of information. And you kind of see that at the bottom. I know it's a little tough to read on this projector. But if you kind of peek through the source code of Pandas, you'll see a lot of instances like this where we're kind of inspecting the type of data that we have to figure out, is this categorical, is this datetime with time zone? And depending on the answer to that question, we may have to take different approaches to handling that data, which is just kind of difficult as you want to add more and more types like this, okay? So before we get into this too, let's talk about a little terminology. We have extension type. And a type, just like Python, NumPy, like concept still applies there. We do allow creation of types using names, which is a little bit different than what you'll see in NumPy, but you could do as type foo if you had a foo type in the system and be able to instantiate your type that way. The main thing that we have in the extension interface is the extension array. So this is where you'll end up writing most of your code if you decide to go down this path and potentially implement your own extension. We don't really make it so that, we don't put a lot of restrictions on how you can construct these, but they do need to be convertible to a NumPy array is the one limitation that we have right now. And if you're thinking of working with multi-dimensional extensions, it's still fine as long as it can be converted to a one-dimensional NumPy array at some point. And I'll show you an example of this later. Because that's essentially what the internals of Panda is going to be expecting. So this is, really an interface to, if you sign up and follow these rules and everything and can convert your data to a one-dimensional NumPy array in some form or another, we're trying to guarantee that the internals will be able to understand your custom type and deal with that appropriately. This last point here, direct from Tom Augsburger, who's one of the core maintainers of Pandas and did a lot of work on the extension interface. What we're trying to move to is make a series a container for an array-like thing. Historically, a series is again, really been bound to like the NumPy array, but we don't want that to be necessarily bound to just the NumPy array. We want to support all different types of arrays. So a series is just a container for an array, whether it be a NumPy type array or array of your own building. So with that, I just want to show you some actual applications. And some of these you can use today on master and Pandas if you wanted to. One of the first ones is integer NA. And again, as mentioned, if you try to store NA data or missing data in an integer array with NumPy, it will implicitly cast it to float. So let's illustrate this up front. Today, your values all the way on the left, let's assume this is a NumPy array contiguous in memory. We, again, cannot store integers in this array because we have missing data. So we have 1.0 as a float, we have a missing value, and we have 2.0 also a float. Pandas is that internals box in the middle, and then to the right you get outputs of certain operations. So sum, min, max, okay, so nothing too crazy going on here. What we do with integer NA is use two arrays, where one is storing the actual values where applicable, and the other is essentially a bit mask of sorts, saying, is this a missing value, yes or no? So compare the two sides of the screen here. Again, on the left you have one array with missing data that has to be a float. On the right you have one array with integer values, doesn't really matter what that middle value is, could be anything, and then you have a mask, essentially saying, is this missing data or not? And with that, with the new extension interface, you can essentially still take that information and define a way to convert that to a one-dimensional NumPy array that the internals will understand and be able to produce the output that you want, being 3, 1, and 2 for sum, min, max. But again, the big difference here is you're working with integer data. You're not getting cast to float. Now, if you're looking closely at it, you may realize that there's potentially some overhead with having a second array to store the mask, and that's true. But we'll talk about that in a little more detail, because if used correctly, you can actually get some pretty significant memory savings through extension arrays as well. But in this case, the big thing you're looking at is precision by not having to cast a float. So how do we actually do this? Well, again, I mentioned today you could do this on master. We have these types in there already, and all you have to do is use a capital I for int. Okay, so just going through the lines of code real quick. On line 3 here, you see a traditional construction of a series of what you want to just be integers with missing data. Your output is not integers by any means. You have the floats and the missing value in between. If, though, you specify the D type as a capital I int 64, you will see that your values are not stored as float anymore. They're still stored as int 64 with that missing value in between. And again, behind the scenes, we really have one array storing the values as int and another storing the mask. But through the extension interface, you can see how this produces the correct output that you want at that point in time. And you can do that with all the sizes, signed and unsigned integers today. So again, I mentioned before, there's potentially a little bit of overhead with having an extra array, but not always. You can actually get some reductions out of this as well in typical usage. So let's say we had some scenario where we wanted to create a series of unsigned int16 values. We'll do it in the range to the high end of that range. So on line 4 here, you see we've constructed our series. Our type is still unsigned integer 16. The moment that we assign a missing value, we've been implicitly upcast to float 64, assuming you're in a 64-bit system. Not cool. Extension array. All right, same kind of thing. All we're doing is declaring an unsigned int 64 with a capital U and the capital I. Internally in Pandas, this is the extension array that can manage integer data with missing values as well. Do the same kind of assignment on line 9 here. I introduce a missing value into my series. It does not implicitly cast anything, so I've kept the same D type throughout. And you can see in terms of the number of bytes used here between line 11, which is the series with just standard integer types, and 12, which is the extension integer types, that the number of, the amount of memory occupied is pretty significant in terms of saving. So you do the math there, you're about 37.5% of what you would have if you had that implicit cast to float 64. Now you could do a lot of other tricks as well to maybe prevent that cast and upcast to 64 bits, but if you just kind of do a normal programming paradigm, that's what you get. So you can, again, also leverage something like this for significant memory savings. Let's talk about another application of extension arrays. This is Cyber Pandas. So this was built mostly by Tom Augsburger, who I mentioned before, has done a lot of work on the extension interface. This is an external package to Pandas, so this is not something that comes with Pandas itself. But what Cyber Pandas does is give you the concept of an IP array. And again, if we go back to that comment about a series being a container of an array-like thing, an IP array is an extension array of just holding IP addresses. Really doesn't matter what's in there. So just, very simply, you see on lines 5 and 6 here, standard construction rules apply. You can build a series of IP arrays and a data frame of IP arrays, so nothing too crazy going on there. Where it gets cool, though, is when you could start using custom attributes, right? So here at the top, you see construction of IP addresses from integer values. And then we have defined, or Cyber Pandas actually has defined, a IP accessor. So you may be familiar with this if you've worked with string types or date time types. There's like a .str and a .dt that you'll see appended to a lot of series. Here it's .ip, and what you can do is define custom attributes like is NA or is IPv6. Right? You see the values there. With the IP addresses, the first one of them is missing. It's essentially 0.0.0.0. That's a null IP address. And then you can differentiate pretty easily between IPv4 and IPv6, again, with a method that you've defined on your extension array. All right, one last demo here. Since we started on the concept of memory savings before, this is one that I've actually been working on. Hence why I put a big asterisk of under development. It's not complete yet, but something you could also take a look at if you're interested to see how this is getting implemented. Bit array. So talking about bit array and taking us back to integer NA really quick. Mentioned that with the existing integer NA implementation, you essentially have two arrays that you're managing behind the scenes, which if you have the same size type could add or will add a little extra memory overhead to what was there previously. But what you can do with bit array, if you're not familiar with the package, is take Boolean masks like you have 0, 1, 0 here. They're all occupying individual addresses in memory. So at least 1 byte that you're dedicating to each of those. But with bit array, what you could do is start working down to bit level. And bit array will do the heavy lifting for you of taking something like 0, 1, 0, which is a sequence of 3 bits, and be able to figure out that, okay, this is really mapping to some kind of array where the second element in the array is true or false or whatever you want one to mean in that situation. So what you see here is you could theoretically, with something like bit array, make your second array much smaller than what it was previously. Take the 8 bits that you have in a byte and really maximize them instead of requiring each Boolean value to occupy 1 byte memory. So this could be pretty significant memory savings. And I mentioned the same points here. One thing I talked about previously was that you just really have to define some kind of serialization from whatever your custom memory storage is that you're doing behind the scenes to a one-dimensional NumPy array. So here's some simple methods. Again, this is under development. I'm not saying this is what they'll end up being, but just to showcase for you. That's literally all that's going on behind the scenes is, we have this mask that's essentially a bit array. We have a bunch of values, and when it comes time to have the Pandas internals start working and interpreting that data, we'll essentially take that and combine it into a one-dimensional array that knows that the second value is missing. The first value and the last value of that array are 1 and 2 respectively. So why would we do something like that? Well, I touched on this before. If you do this correctly, you can get really significant memory savings. Again, we've taken that second array, which was just a mask of 0 and 1s, and you can reduce the memory footprint of that by up to a factor of 8, simply moving from bytes to bits. Let's say you had, instead of an integer array, you had a Boolean array backed by a bit array. So you wanted a Boolean array that could store NA values. You could theoretically have 2 bit arrays, which would essentially give you all that same information that before you would have to store in a really expensive float 64 array. So something like that could save you up to potentially 16 times the amount of memory that you would have just by having some kind of extension array interface like that. So Those are just some quick use cases. Again, I wanted to familiarize you with this. Not necessarily going to go too deep into the actual implementation, but if you are interested in learning more about it or seeing more, obviously the Pandas documentation is a great place to start with that. There's also extension arrays for Pandas, which Tom Augsburger wrote, kind of the initial article that introduced this whole new interface, so you can see what's going on there. And I've also provided a link to a talk by Uwe Cohen, where he kind of goes in a little bit more detail about, what are the things that you actually need to build out in your extension type to make sure that you can interact with the interface and, build your custom type or your custom memory management underlying the arrays that you'd like to report off of. And with that, I'll take any questions that you have.
Thanks for your talk.
Yeah.
What are you storing in your integer array? I assume it's not a question mark for the missing value.
Honestly, I don't know. I don't care.
But there has to be something there if you're using an integer array.
Yeah, I think it could just be any kind of sentinel, or it could be a value that you really just don't care about. I'm not sure. That might go that's probably a little further into the metal than I've actually looked at myself.
I see. But I don't see how you can know what integers the user doesn't care about.
That would be the mask, right? The mask tells you I don't care about that second. So if you think about those two side by side, and again, when you actually get to the point where you're like condensing them down into a one-dimensional array, that mask is your indication that whether it's 0 in that question mark or some other kind of sentinel, like it really doesn't matter. Like that's an instruction to the end user that's the missing value. So that's where you really start using, 2 arrays to kind of get at that, get around that limitation that you can't store any data in a integer array in NumPy.
Cool, thank you.
Yeah.
This is really cool stuff. I'm excited for it to land.
Yeah.
My question was around, are you aware of anyone working on this in the area of making text perform better? I know that text being, sort of strings being an object D type has been a pain as far as memory usage. Are you aware of like?
I'm not personally aware of anything going on, but I wouldn't be surprised if that's an area that people really focus on because, there are a lot of limitations to working with string data and just having it generically stored in an object type in Pandas. So there's certainly a lot to be done there. Kind of our hope, and actually this is a really good question, like our goal is not to put all of these items into Pandas per se. Like we want to have a library of like external packages that, the community could contribute certain types of extension arrays to. And you saw that with Cyber Pandas. I think, don't quote me on this, but I think AstroPy or some of the people with that might have done something to give you a unit of measure with each of your arrays, which is super important in astrophysics, but also a lot of applications. So there's nothing internal to Pandas right now on that front, but we'd love contributions if it's something that you or anyone else in this room is thinking about. This is really the way to do it. And again, it doesn't need to be done in Pandas. We would love to have a library of external packages that can kind of focus on particular aspects of data processing and management.
This might be a bit unrelated. One of the last link was something about Pandas and Arrow and NumPy. So is Arrow something will come inside Pandas or has to be an external library?
Well, Arrow is an external library. Wes McKinney, who started Pandas however long back.
Sorry, I wasn't clear. Will the support for Arrow be built inside Panda or will it be an extension? That's what I meant, sorry.
Yeah. I don't know exactly how that implementation is going to work out, but we do want to start supporting that more. I mean, you can kind of read it through the certain formats today, but long term it would be great to use that memory format as well. I don't know if that is going to be an extension array or just kind of the implementation that we move towards internally over time. But however that actually gets implemented, there's certainly a long-term vision to move towards Arrow to start working with some of the internals and using that for memory management.
Thanks.
Yeah.
Thank you for the talk, Will.
Yeah.
If you can go back to the slide you were on earlier where you show the mask array and the internals box.
This one.
Yeah, or the previous one.
Oop. Back one more. Yep.
Yeah, that's fine. So, so in this example here, you're going from a vector to a scalar value, right? What happens if after the internals box processes the data, I again have a vector?
Yeah.
Don't I need a mask on the other side as well, or what happens? Yeah.
Wait,
so,
okay. Yeah, the goal there would obviously be to preserve the D type that's coming in. So if you're sending in a D type here of like the integer NA, we would love to return an integer NA as well. Yeah.
Right, but then you need to preserve the second element in there.
Right. So, and again, think about it this way, like you're kind of more or less serializing your integer NA when you pass it to internals. So the same way that you have to send it into a NumPy array for the internals to process, you have to be able to understand that NumPy array that gets returned when it comes back. So it's more or less on the extension author to be able to handle that. But the goal is, again, as long as you can like convert to a NumPy array, you could theoretically losslessly come back from it, which the Pandas internals would give you. So if the extension is coded correctly, and instead of aggregating to a scalar or something like that, you get a series or whatever, you'd still, the internals as is today would give you a NumPy array back, and then your extension array would understand how to essentially deserialize that NumPy array back into your original implementation. Mm-hmm. Yeah.
So if I write my own type, do I get this mask to represent missing data right away?
No, this mask is something you'd have to implement yourself. So if you actually look in, and as I mentioned with the integer NA stuff, it is already actually in Pandas master. So if you look at pandas.core.arrays in the source code, you'll see how it manages that. But it's not like you just automatically get a free mask, because not everything needs a mask either. Like we're going to have extension types that don't work with missing data per se. So that's not something that's guaranteed. It's something you as an author have to code in yourself.
Thanks.
Yeah.
Have you guys already played with whether different extensions are composable or able to both be applied to the same item? Like, for instance, you needed IP addresses where NA is also required.
Can you repeat that question? I don't know if I fully understand.
When you start using one of these extensions, are you pretty much locked into doing things the way that extension does? Or if you have the need for two different behaviors that are provided by two different extensions, is there any way to have them both?
I don't know if the internals of Pandas would be able to guarantee anything about that. I assume you could do some kind of composition with another extension that would be composed or inherit from two other extensions in some form or fashion. But I guess, so your example, like you're asking if you wanted to store like missing values, like instead of storing it as 0.0.0.0 for the IP address, like you may want to store it with a mask instead and kind of compose that from an existing IP type and
Sure, that's a better example.
Okay, yeah, you could do something like that. I think that burden would kind of fall back on the extension author to be able to handle something like that. I don't think Pandas is going to do anything internally to kind of infer or compose types from various extension types, but certainly as an author, I think you could do something like that. Yeah.
So it looked like if you wanted to use your own types in a single series, it seemed pretty straightforward. You could use dtype or you could use as type. How does that work if, like you were talking about bit masking between multiple columns, how does that work?
Bit masking between multiple columns.
Or not bit masking, but yeah, bit masking. Like if you had a series of true-false booleans and you're using one integer to store it, how would that work?
Well, keep in mind that you're going to be, we definitely want to separate like the work that we're going to do in the extension land from like the Pandas user-facing end. So if you go back to an example like this, like I think line 6 is more or less what you're talking about, right? So, you know, compare lines 3 and line 6 here. Line 3, you know, you're trying to inject missing data into a series, and essentially you're getting coerced into float 64. Now, if you wanted to construct something that was like true, missing, false, true, missing, you would essentially do that similar to what you do on line 6. You'd say, build me a series of true, false, NA, true, false, whatever. D type's going to be bool NA or whatever that extension type is called. So that all, again, from like a Pandas user perspective, should be seamless. Now, the extension should be responsible for being able to interpret, you know, what those values are. And in that case, I think I just said like 6 values. Like you're going to have a mask that, you know, is noted in 2 places that there's a missing value, and wherever else it's going to store the actual Boolean value. So your extension array will implicitly like be able to take something like this, as long as it's implemented correctly, and store that internally in the memory format that it needs. But I just want to be clear to like, you know, you typically wouldn't want to directly instantiate like your extension array. I mean, you could, like you've seen in Cyber Pandas here, like IP array is an extension array. We're instantiating it directly and then kind of passing it to Pandas. But on the flip side, if you're just a general Pandas user and, you know, just want that to work automatically, you can do it directly through a series constructor. And as long as the type is specified as part of that, you know, that should start firing off and interfacing with your extension appropriately to make sure that that data gets stored the way it needs to. Does that answer your question?
Yeah, thanks.
Yeah. Anything else? Cool. Well, thanks everybody. I appreciate you coming by.